Hello everyone, it's time for class again. This is ECE341, the probability and the random process course. Welcome. ECE341, this is the third week Monday's class. Okay. Last time we have introduced the concept conditional probability and independent events, right? So we have this one is a conditional probability that is a probability of event A under the condition B. B is a condition. Suppose B is happen, then in this condition, under this condition, we check the probability of A. This will be probability of A intersection with B out of B. This is you consider things like B the whole sample space. So you check the probability out of B. Okay. And independent. Now we need two events. We say A is independent with with B. What is the meaning? That means the probability of A and the probability of A under condition B, they are same. So whether do we have B as a condition, the probability of A are same. Okay. Now we want to find if we combine these two, because this is A under condition B, this is also A under condition B. So we have these two are same, right? So we say A and A is independent with B means probability of A equal to probability of A intersection with B over probability of B. And we have this one. So we have A is independent with B means PAB equal to PA times PB. Now we have a formula like this. This is a kind of symmetrical, right? Symmetrical. The A and B, they are in the same level. Probably A times probably B. Here's a different, right? This is in fraction. Here they are in the same location. They are times these two, you get PA intersection with B. So independent, you can also see this one. Then we can reverse the order. Here you use B as a denominator, right? B as a denominator. Now we can use A as a denominator. So we can have A is independent with B means probability. Now I use A as a denominator. So PB equal to PAB over PA. I just change the location. And this one, now we still use this one, but now A is condition, right? This is PB under condition A. So we have this. And the first one we get this one, now we get this one. So you see, A is independent with B. We have this one, PB equal to this one. And by definition that means, so B is independent with A. You can you can say in different order, right? A is independent with B, that means B is independent with A. Alright, then we can say A and B are independent. Okay, by definition, when you define the independent, you need to consider B as a condition. And then you can find this equation you can write in different way. Now A is the condition. Then okay, so both A and B could be condition. So we can say A and B are independent. If you use A as condition, whether A happen or not, the property of B will be same. And another way, use B as a condition. No matter B happen or not, the probability of A are also same. Alright, so this is the independent of two events. I think we have a example last time, right? We roll a dice 2 times. 2 times. Then we have the result looks like this. The first time, second time. First time we can have 1, 2, 3, 4, 5, 6. And second time we also have 1, 2, 3, 4, 5, 6. And between then each one will be some I and j, right? So the sample space will equal to all these I and j, where I will run from 1, 2 until 6. J is also run from 1, 2 until 6. Right? So we have sample space look like this. And each probability is 1 over 36. Suppose this is a fair one, fair dice. Suppose this is a fair dice. Then we have this, right? We have the model looks like this. And I choose 2 events. One is A, one is B. Okay, A is like I forgot which one I used. Anyway, suppose A equal to I use I equal to a number, I equal to 3, and the B is J equal to 3. Alright, then we check whether they are independent. Or not. Are they independent or not? Okay, you need to do calculation. So here we can calculation probability of A intersection with B. Then this one is what? This is a probability of, because both A and B happen. So this is just A is 3, I is 3, J is also 3. Right? It is this one. So it is 1 over 36. 1 over 36. And the probability of A, that is a probability of I is 3, and J could be any. So J run from 1 to J 1, 2, 3, 4, 5, 6. So totally we have 6, right? We have 6 numbers. So it's 6 times that 1 over 36. This is 1 over 6. It's a PA. And PB, B is a now I can be anything. J is 3. So this time I equal to 1, 2, 3, 4, 5, 6. So totally we have 6 samples. 6 samples. Each 6 samples. Each one the probability is 1 over 36. So the other 1 over 6. Right. Okay. Now we say PAB equal to PA times PB. right? 6, 1, 6, 1, 6. You times them together, you have 1 out of 36. So you have this one. All right, now you can claim A and B, they are independent. Right, they are independent. Yeah, because this one. Of course, you can also calculate, we have 3 formulas, right? We have this one, we have this one, and we have this one. We can also use this one or this one to determine whether they are independent. We find this probability and compare with PA. Yeah, we can also do that. So we can see, or probability of A under condition B. This is a PAB over PB. B is the condition, right? And the PAB we just have PAB is 1 over 36, and PB is 1 over 6. 1 over 6. So this is also 1 over 6, right? 1 over 6. Yeah, you get it? Make sure. Yeah, you can like this. 1 over 36 times 36, and 1 over 6 times 36. Then you have numerator is just 1, and denominator it is 6. Right? You can calculate by this way. Yeah. Okay. So this is 1 over 6 equal to the probability of A. So we have PA under the condition B, this probability, conditional probability, equal to the probability of A. So we say A and B, they are independent. Independent. Right. Yeah. So all these ways works. You use this formula or you use this formula, and you can also use the other one. Use A as a condition. Right. There's a PB on the condition A equal to PB. You check that. Then we have these, so it is independent. They are independent. All right. So this is how to check the independent. Okay, now we want to consider something more general. If we have 3 events, can we have the independent? Can we have the concept of independent? Suppose we have 3. Okay, I still use this one. A, B. Now I consider C. Now I consider C. Let C equal to, I see also I want 6 element, so I want this one. I plus J equal to 7. Yeah, you can see this. This is C. This is C. Actually, this equal to, if I is 1, then J should be 6. Right? If I is 2, J should be 5. Right? 2 plus 5, 7. And 3 and 4. And 4 and 3. And 5 and 2. And 6 and 1. Right? So totally we have 6 elements in C. We have 6 elements in C. So we can have the probability of C, which is 6 times that 1 over 36. I have 1 over 6. Okay, so this is a C. Now we consider C and A. Are they independent? We check C intersection A, the probability, which is what? C is I plus J is 3. So we have totally have 6 of them. And A is I is 3. Right? A is I equal to 3. A is I equal to 3. Yeah, I read this. I equal to 3. I equal to 3. So here you see which one is I equal to 3. We already have these 3 and 4. So this is a probability of it is just 3 and 4. This is the intersection of C and A. Only one element, so the probability is 1 over 36. And we know this equal to 1/6 times 1/6. It is equal to PC times PA. Right? PC is 1/6. PA is also 1/6. PA, yeah, PA is also 1/6. So we have these. We have these. Then we can claim C and A, they are independent. They are independent. Alright, you see, we know A and B are independent. A and C, or C and A, they are also independent. Now we check the third here. We also can have C and B, right? C and B. Okay, C and B. So we consider the probability of C and B, the intersection of C and B. Now what is C? C is a summation equal to 7. And B is here. J equal to 3. So this is should be 4 and 3, right? I and J should be 4 and 3. So the probability, it is 1 over 36. Just one sample in the whole sample space. And this is just 1/6 times 1/6, and it is a probability of C times the probability of B, right? Okay, now we can claim C and B, they are independent. They are independent. Okay, now we have A, B, C. The any of two of them, any two of them, they are independent. Independent. Okay. Any two of them, they are independent. A, B independent. B, C independent. A, C also independent. Okay, can you see all of them, they are independent? Well, we consider this. But now, consider we say the probability of A on the condition B with C do intersection. So this time we suppose both B and C happen. Both B and C happen. We want to see what is the probability of A in this condition. Right, this is also a conditional probability. Under this condition, what is A? What is A? Okay. Now we start by definition. P of A over BC equal to, firstly we should know what is BC. BC is the intersection, it's just this one, right? BC is just CB. So it is just 4 and 3. I is 4 and J is 3, BC. And the probability of BC is 1 over 36. Right, we already have these. And this by intersection is a P A intersection with B and C over P B and C. So here I also need the intersection of A, B, and C. What is A, B, and C? We need three conditions. 3 out of 3 happen. So I need I is 3. J is also 3, right? And I plus J equal to what? 7. Oh, can we have it? I say no way, right? No way. You have I and j, there are 3, the summation is 7, so this is nothing. Empty. So we have P, A, B, C. This is just the probability of empty, that is 0, right? This is impossible. And then we have P, A on the condition B, C is 0. 0 over P, B, C, right? 0 over 1 over BC is what? 136. So this is 0. Okay, you see? Now you check the independent, right? A, B, C, they independent each other. You take 2 of them, any 2 of them, you use one as condition, you check the probability of the other one, then with or without the condition, doesn't matter. So they are independent. So use B as condition or not use B as condition. Probability A is same number. But when you use both B and C as condition, you check the probability of A, now you get 0. This is a different value, right? We know P A is 1/6, right? We have this, do not equal to 0. So that means you use B and C, they happen at the same time as a condition. The A will have different probability. Now it's 0, not 1/6, right? No 1/6. So we'll say A is not independent with the intersection of B and C. Okay, now we have the idea. When you look at 3 events, you want to check the independence of these 3. You have 2 ways to think about it. One way is you think it peer by peer. So like this, you look at any 2 of them, they are independent. But if you look at all of them together, you use like B and C together as a condition, B intersection with C as a condition. Then this A will be different. The probability of A will be different. With this condition BC, you get probability 0. Without the condition BC, you get probability 1/6. So it's different. So we cannot say A is independent. A is not independent with BC. Alright, now we have our definition. For A, B, C, 3 events. If PA, B, C equal to PA times PB times PC and PAB equal to PA times PB and PA times PC equal to PA times PC and now is B. BC equal to PB times PC. Then we say A, B, C, these 3, they are independent. In this case, use B as a condition, you can have same probability on A. With or without B as condition, probability of A is same. Or you pick any one as a condition and consider the other one's probability, they will be same, no matter do you have or do not have that condition. And then you pick any 2 as a condition. Now these 2 happen together. You check the probability of the other one. Then it will be also independent. no matter do you have the condition. Okay, so in this case, we can call these 3 are independent. So this is I would say this is stronger than just 2 of them are independent. Yeah, you even use any 2 of them. If you use combine of them as condition, then the probability of A is also same. Okay, so we call these 3 are independent. And independent of these 3, we have to have these 4 formulas together. And more generally, this is a 3 event. For events A, B, C, D. Now we have 4 events. So we see that both are same. Now we have more. We have all of these, 2 of them, 3 of them. We also need to consider 4 of them. And the 2 of them, you need to use all of these. A, B, A, C, A, D, B, C, B, D, C, and D. There's a lot of formula. So we can see this. If any 3 of them, right? They totally 4. Any 3 of them, they are independent. That means that 3 satisfy these 4 formulas. If any 3 of them, they are independent, and the largest one, the most of, all of them, A, B, C, D, you put them together, equal to PA times PB times PC times PD. Then we say A, B, C, D, they are independent. Alright, yeah. So this is independent of events. Do we have any more example? Actually, here I have an example. I have three events, and they are not independent. And in 2 of them, they are independent, but 3 of them together, they are not independent. Right? I have two times. I roll a dice 2 times and check the summation equal to 7 as an event. And the first is 3 is an event. The second is 3 as another event. And then they are independent. These 3, the independent pairs, pair by pair, independent. But you put 3 together, it is not independent. Right? Can we have examples? 3 of events, they are independent of each other. Yeah, we can use this one. We have this example before, right? Similar example we have. Example. Consider 3-bit binary code. And the sample space is I, J, K. Now I equal to 0 or 1. J is also 0 or 1. And the K is also 0 or 1. Right? And we suppose all these 3 numbers, they have 0 or 1 equal likely. Equal likely to have 0 or 1. Okay. So this is a sample space, right? Sample space, we have how many? We have 8, right? Total you have 8. We have 8, 3 bit, right? This is 8. And then I use AI equal to I use I is just A. Okay, A is I equal to 1. B is J equal to 1, and C is K is 1. So are they independent? I think they should be independent, right? The first bit is 1, and the second bit is 1, or third bit is 1. They should be independent, right? But we need to do a calculation to check it. So we have A. Actually, first is 1. Then yeah, we just check that. This one, how many do we have? How many elements in A? The first one is 1, and second and the third, J and K any, right? So it will be 1, J and K. So this is A, and the whole amount of these will be, this has 2 choice, this has 2 choice, so it will be 4 choice, right? 4. And similar, B is also 4. C, the amount of C is also 4. And each element, because they are equal likely, so each element will have probability 1 over 8, right? 1 over 8. So we can have PA equal to PB equal to PC. They are 4 times that 1 over 8, so it is 1/2. Each one has probability 1/2. Okay. And then we want to check PAB intersection PBA BC and PCA, and finally we check PABC, right? We check the probability of these, all of these, and we will see do they satisfy this one? Do they satisfy these four equations, right? All right, we can see what is the PA intersection with B. That means first bit is 1, second bit is 1, so it is a probability of all of these. First is 1, second is 1, and the second, then the third one, K could be 0 or 1, right? Like this. So we have 2 choices, right? Totally we have 2 elements, 1, 1, 0 and 1, 1, 1. So the probability should be 2 of 1 over 8, that is 1 over 4, right? And similar, BC, B is J equal to 1, C is K equal to 1. So this time we have a different I. You can choose different I, but the J is 1, K is 1. Right? Now it's I could be 0 or 1. And we have 2 elements, so this is 2 times 1 over 8. We have 1 over 4 again. Alright, and CA, this is a probability of, now is a I have A, so the first one should be 1. And B, no B, but I have C, so the third bit is also 1. Here J could be any. So this is also 2 elements. Each has probability 1/8, so I have 1/4. Alright, the last one. This time I have I is 1, J is 1, and K is also 1. Okay, just 1 element. So this is 1 over 8. 1 over 8. Okay, do we have the equations? So we have PAB equal to PA times PB. Do we have these? Yes, right? PAB is 1/4, and PA is half, and PB is also half. So half times half get 1/4. And similar, PBC is also 1/4 equal to 1/4 equal to half PB is half, and PC is also half. Right? No problem. And CB, this is a PC times PB, right? It's still half times half equal to 1/4. And the last one, PABC equal to P A times PB times PC. Can we have these? Yes. Yes, right? Half, half, half. 3 half times together, you get 1/8. 1/8, right? This is 1/8. So we say A, B, C are independent. So this is an example when we have 3 bit. Actually here we have assumption. We say all of these they're equal likely, right? So we have this result. If the probability of these IJK they have some other restriction, other condition on it, then we do not know can we have this. You need to check. You need to check all of these and certify whether they satisfy these equations, right? If they satisfy, then you can have this result. Alright, yeah. Okay, so these are the independent of events, and we have another concept we call it independent experiment. We say independent experiment. Experiment 2, I see. Right, it's kind of way. You have a sequence of event. We consider example first. Example. We have some like 5 blue bars. I have another 5 red bars. I put all of them in a box. The bar, they have same size, made by same material. So if you just touch it, you do not know whether what is the color of it. So now you pick a bar outside the box. Pick one. Pick one. You will have result will be blue or red as a result, right? So this is an experiment. You pick a bar from the box, and the result you check the color of it. Okay, if you just do one time, then you know you have the sample space or equal to just the blue or red, and the probability of V or probability of R, because both they are same, right? 5 and 5, totally 10. So 5 out of 10, or just 1/2, half and half chance. All right, now we do the experiment sequentially, right? We do first time we pick a bar, and second time we pick the bar again. Okay, pick one again. Pick one again. But before you pick a new bar, you already have one bar out, right? You already have one bar out. If you place the bar back, or you do not put the bar back to the box, then things are different. Re-put, right? Re-put back. We will put back pick the bar. Then we will say still same as, right? S is still same, no matter you pick or doesn't matter. S in both cases, S will be same. S will be same. You re-put the bar back, then you will have PB times PB and PR are same. But do not put the bar back. In this case, you have PB. Well, it depends. You don't know. It will be something different. PB and PR different, right? If you have a blue bar in the first time, then that means you only have 4 blue bars left in the box. So next time when you pick the bar again, you will have less chance to get a blue bar. Okay, if it's in other hand, the first time you have the red bar, in your hand, then this time you only have 4 red bar in a box. So when you pick the bar, you will have less chance to get red bars. So PB and PR, they are different. And before you perform the first time experiment, you cannot sure what will be these 2 probabilities, because they depend on the first experiment. So you can consider now we have 2 experiments, right? The first experiment, just pick bar from here, and then we perform the second experiment. We need to still pick bar from here, but the number of these bars are different, right? So we have, in this case, this is independent experiment. True. Yeah, you can repeat it, right? You pick a bar and put it back, and then do it again. Pick a bar and put it back, and pick a bar and put it back. Whatever, you can try as much as you want. And the second way, this one, you pick a bar but you do not put it back. So this is not an independent experiment trail. Yeah, in both cases you have a sequence of experiment. But in first case, each time you start in the same condition, right? Every time you still have 5 blue and 5 red bars in the box, so every time the totally same. So they are independent experiment trials. They have same sample space, same probability distribution, right? And the second kind of experiment trail, every time because you pick a bar and do not place it back, then the probability of these 2 will be different. And even after a while, there's no bar in the box. No, for example, no blue bar, you still have some red bar, or you have some blue bar but no red bar. Then the sample space will change, right? Suppose all the red bar were removed from box, you only have some blue bar inside the box. Then in that case, the sample space change to be only contain B, no R, right? So even sample space will change. And finally, you pick all the bars outside, no bar in the box. Then you cannot keep working on that. This one you cannot repeat all the time. You repeat for a while, then you're done. You cannot do any more experiment. No materials, right? Yeah. So this is the second case. Okay. Anything more? Okay, one more thing. For the independent, actually we have 2 kinds of independent. The first one is for event, second one is for experiment. They are similar thing, but they are different. Okay, all right, and they are related. In like this case, the first experiment will change the second experiment's the distribution of the probability, right? So you can think this is kind of things. You consider first experiment as a condition. You can check the probability of the the event in the second. You consider the event in the first as condition, and you check the probability of the event in the second experiment, right? Yeah, so you can still consider like that. All right, that's all for today. See you next time. Bye bye.